Hello and welcome to another episode of the Avid Technology Podcast with me, Ryan Morn. And today's episode, we're going to do a bit of a deep dive technology-wise on a couple of vehicles that have been making a lot of waves in the press recently. So a huge amount has been written about the new Porsche Taycan and the Audi e-Tron. And of course, there's been an awful lot of comments about their relative efficiency, particularly compared to the Tesla Model S. There's other fully electric cars out there that have also been compared to Teslas, which seems to be the thing to do, such as the I-Pace and the Mercedes EQC. But for the purpose of this episode, I'm going to home in on the Porsche and on the Audi, and we might come back and look at the others and do a technology review on those at a later date. So I thought it would be really interesting and answer quite a few questions if we just did a kind of technology deep dive on these cars. Basically, a lot of people are saying, how is it possible that the German OEMs have missed the target in terms of efficiency and range so badly compared to actually what is quite an old car now in the Tesla Model S? The American business not having anywhere near the resources and the engineering firepower that the Germans have. And it's interesting that the cars have come to the market at this time, and obviously that's the immediate comparison that's been drawn. Porsche delivers amazing performance. I mean, it's absolutely blistering. 0 to 100 kilometers per hour in 2.8 seconds. That compares pretty well to a Tesla, which is about 3 seconds without ludicrous mode engaged and about 2.4 with. Fairly evenly matched in terms of straight line acceleration. This level of performance, for me, it's way beyond what is usable for the average person on, or even a not average person on a day-to-day driving basis. In fact, it's beyond what is safe for a normal person on a day-to-day basis. I think you would make yourself feel pretty sick quite quickly if you're using either of those cars to the full extent of its performance capability. There's also been a lot of discussion around the rated range and, considering the relative cost of the cars. So the Tesla Model S long range has a WLTP range of 365 miles or 325 on the EPA test cycle. The Porsche Taycan Turbo S, it makes my skin crawl even saying that, because obviously it's not a turbo, but the marketing guys clearly got a bit carried away with themselves there. So I might I don't know how I'm going to deal with that later on in this. So the Turbo S Porsche manages 265 miles WLTP, and actually the Audi e-Tron's got a fairly similar range, 248 miles WLTP. That's a huge difference to the Tesla. So 100 miles difference, around 30% difference on the range. And, people are rightly asking what's the reason for such a huge difference in range? The manufacturers have come out and made some comments themselves in terms of where they think it's coming from. And in this podcast, we're going to explore that in a little bit of detail. So, first starting point on these cars would be really thinking about the battery capacity. So the Tesla has got the biggest battery, 100 kilowatt hours installed capacity on that vehicle. The Audi is a little bit behind that with 95 kilowatt hours installed capacity, and then the Porsche has 93.4 kilowatt hours. So just purely from installed battery capacity, you would expect some difference on range, but not such a huge gap. I think the difference of 30% does look like a bit of a big problem with powertrain efficiency on these cars. So, just looking at that, there's a difference between the range and the efficiency, and that's, I think, obvious, but I think some commentators in the press have got a little bit confused around this and carried away. So obviously, the efficiency of the car is how much energy it consumes to drive 1 mile or 1 kilometer, normally measured in something like watt hours per mile or kilowatt hours per 100 miles. So that's the efficiency measure. So how much energy are you using to drive 1 mile? Then the range is basically a function of your battery capacity over your efficiency. So you get a certain number of miles out of that battery. So a more efficient car will go further on a given size of battery. The two things are connected in terms of what drives efficiency, but they are different. And it's important for us not to get too sort of into that. So Tesla's got a bigger battery than the other two. as installed capacity. So you would expect it to go a little bit further anyways. But that might account for kind of 5%, not 30%. So really, what is it? Where is the rest of this difference coming from? I think that there's quite a big difference when you look at then the usable capacity on the battery pack. So people kind of phrase this in different ways, but basically what the manufacturers do, so they have an installed capacity, so a nominal kind of maximum capacity for the battery pack, but they don't let you use all of that on a day-to-day basis. And actually, when you look at the numbers, it's fair to say that Porsche and Audi are both walling off significantly more of the battery capacity than Tesla do. On Audi, the headline battery capacity, as I mentioned earlier, is 95 kilowatt hours, but the usable capacity is 83.6 kilowatt hours, so quite a big gap there. Porsche, similarly, 93.4 kilowatt hours, but only a usable of 83.7, so less usable onboard storage. The Tesla having its 100 kilowatt hours, but then a usable of 95 kilowatt hours. So the gap, the delta between the maximum capacity and the usable capacity on the Tesla is much smaller than on the Audi and on the Porsche. So next question is, why do the manufacturers do that? Why do they not let you have access to the full battery capacity? There are, in fact, several reasons for this. The two main ones, though, I think, being consistent brake feel. So people might go, that doesn't make sense. Why has it got anything to do with the brake pedal feel? Well, in an EV, you have regenerative braking. So when you press the brake pedal, part of what is doing the work is the pads, making heat and wasting it on the disc. But actually, most of your braking should be coming from regenerative braking. And in that process, the electric motor that drives a car turns into a generator, and you're putting power back into the battery. The problem with that is you can't put power back into a full battery. So if the battery is completely full, then you'll have to turn regenerative braking off. And in that case, you would get basically an inconsistent feel in terms of the brake pedal. You would notice the difference, even with the best software in the world to manage around that. You would notice the difference in the brake pedal. I think Audi and Porsche, being who they are, they really value that very, very consistent braking feel. So they will have done some calculations and they'll have worked out every possible scenario on the planet, and they will be allowing a certain amount of battery headroom to make sure that under every single driving condition possible, you have consistent brake pedal feel, and you never have to turn the regen off or down because you're approaching maximum capacity on the battery pack. So that will be part of the reason for it. Now, this problem itself can be completely got away from if you employ a braking resistor. So you basically put some stuff into the powertrain on the car to take power out of the system and effectively burn it off if you're braking when you're close to full battery capacity. So in commercial vehicles, in larger vehicles, that's quite a common thing for braking resistors to go in there. Passenger vehicles, not so much. There are other things that you can turn on and off, but it's really part of the really delicate part of the system balance, making sure you have a consistent brake pedal feel, and that's part of the reason why they have a bit of that headroom in the pack. The other reason, there's kind of 3 or 4 ways you could describe this, but I'm going to go for cell longevity, especially factoring in rapid charging. So, people who drive an EV now will know when you go to a rapid charger, you typically can't charge the car to 100% full in one session at the charger. Now, that is because the rate at which you can push current into a battery pack will reduce as the battery approaches being full. So you have to get a bit more careful about how you charge it the closer it is to being full. And I think that what the Germans were aiming for here was a very consistent charging experience for the customers. So they wanted to be able to charge really quickly all of the time. The other thing, of course, here is that this sort of property is exacerbated by temperature. If it's hotter, then this problem gets worse in terms of battery degradation when you're fast charging it close to being full. Actually, if it's really cold, you can have a similar kind of problem. And I know that the OEMs, the German OEMs, have been talking a lot about charging performance at the press launches and such like. And I do wonder if that's been a key metric that they've been designing the car to. So basically, they've kind of walled off more capacity of the pack than they need to, But in order to make sure that there is a more consistent performance of the pack during charging and a more consistent performance of the car during braking, so it's all about consistency, and that probably goes somewhere into the brand values of Porsche and Audi, and people who know those products well know that kind of thing is really important to them as a company. Now, I do think there are a couple of other features there which I'll get onto later, which have an impact particularly on this second one. So battery cell longevity in terms of the design of the battery pack, because there are some pretty big differences there, and I'll get into that later in this episode. But for now, we'll move on. So if we look at the per kilometer efficiency rating, so I said earlier, there's a difference between the range, pack capacity, efficiency of the car. So we've already established we've got much more usable battery pack in a Tesla than we have in the Porsche and the Audi, and that will go a long way towards explaining the difference in terms of the range performance of those cars. So that's, in the Audi's case, probably accounts for half of the difference in the range. But the rest of this comes now from looking at the efficiency rating of the car, so the amount of energy that we use per mile or kilometer traveled. And the figures on this, I've kind of had to do a lot of searching around, and I know that I've put this out and I'll immediately have people correcting me or getting it wrong or whatever, but I've tried to be as diligent as I can in terms of getting the right information, the right baseline information to compare them. So I've gone for the WLTP efficiency figure, and the Porsche is 230 watt hours per kilometer. So that's not bad. The Audi is 283 watt hours per kilometer, which is actually quite poor for the kind of car it is. And the Tesla is only 210 watt hours per kilometer, and that's pretty impressive, for a larger car. So you can see there already. So the efficiency in terms of the driving efficiency is significantly better for a Tesla than it is for a Porsche or for the Audi. And you look at something like the Hyundai Kona, so a smaller car, 155 watt hours per kilometer, going on the same measure. So the Tesla's good, but actually there are cars out there that are better in terms of their efficiency, just not the Audi or the Porsche, unfortunately. So we can see from that the Porsche and the Audi are using more energy per mile or kilometer driven than a Tesla. So that is the rest of the balance. So I could leave this podcast there, but I thought what would be interesting was then to look at why that is. So is it easy for us? A lot of people have said, the efficiency of the Porsche motors is terrible. The efficiency of the Porsche powertrain is terrible. So what is it? What can we look at here in terms of working out what is driving that difference in efficiency? And I guess, crucially, is it something that in the real world will show through? Because we all know there's a difference between the rated efficiency and real world delivered efficiency figures. But is it going to make a difference to you on a day-to-day basis? So we've talked about this before on previous episodes, interviews and white papers, in fact, in terms of what drives the efficiency in an electric vehicle. And basically, there's 5 key areas. You've got the battery and the charging system. That's really important, particularly the charging, because you measure the energy loss in the charger when you're going there. Next is the efficiency of the traction motor and the power electronics. So how efficiently can we convert stored electrical energy into movement in the motor and the electronics. Next is the ancillary systems, so cooling and HVAC, so keeping the occupants nice and cozy, and keeping the powertrain at the right temperature. Now, that's something that the German OEMs have made a big deal about in terms of their cooling system, kind of embedded power being much better than the Teslas. The 4th key characteristic is aerodynamics. So how slippery is it? How easily does it cut through the air? And there's some clear differences there. And finally, we've got vehicle weight and rolling resistance. So putting those two things together, very closely linked. So I think to start with this list, we're going to go in reverse order, because it's basically the easiest to deal with. So the weight in the Aero first. So the Porsche is 5,100 pounds. It's a little bit heavier than a Tesla, 4,900 pounds. The Tesla's not exactly a light car for what it is. The Porsche isn't either, so a couple of hundred pounds heavier. The Audi, though, is much heavier, so 5,750 pounds. So clearly there's an advantage to Tesla there in terms of having a lighter vehicle. So a lighter vehicle needs less energy to accelerate it to a given speed. Taking out the powertrain and battery weight, it's a big topic for future EV development. So if anyone sort of wonders why people want to make motors lighter and electronics lighter and battery systems lighter, basically every kilogram, every pound you can shave off the vehicle weight will help you from an efficiency point of view. It will reduce the amount of energy that you need to drive the vehicle per kilometer. So Tesla has a clear advantage here, and I think we can explain some of those differences later on. Obviously, the Audi is a kind of SUV type vehicle, so maybe you could argue it's not a fair comparison to make, but it is a comparison people are making, and it's clearly a little bit podgy there. The Porsche, even that difference, 200 pounds, so about 100 kilos difference, that is significant for this kind of vehicle. In the Ice Age, people would literally kill to take 100 kilos out of the weight of a passenger car. That's worth a lot of fuel consumption or energy consumption for an EV. So next, if we look at the Aero, Tesla is basically better at slipping through the air. Now on this, interestingly, Porsche kind of straddles the Tesla. So I have to say it again, the Turbo Turbo S has 0.25 CD. The Tesla is 0.23, but the vanilla Porsche is a 0.22. So obviously some of the kind of body kit and wings and stuff of the Turbo S Porsche are making it a bit less slippery and causing a bit more drag. So, 0.22 to 0.23, that will make a difference in terms of the amount of energy you need to push that car through the air. The slipperier it is, the less energy it will need. The really interesting one here is when you get onto the Audi. So 0.28, that's 20% more than the Tesla. And that is, that's significant. Pushing through the air is one of the most significant energy consuming things on a car. So about 2% fuel saving per 10% improvement in CD, drag coefficient. So just from the difference in drag coefficient between an Audi and a Tesla, we've got already about a 4% difference in efficiency of the car. So if we go back to the numbers earlier, we're looking for about 30% overall difference in terms of the range. We can explain basically half of that difference through the reduction in battery pack capacity. Then the other half, so about 15%, is from the efficiency of the car. And about 4%, so a third of that is between the Audi and the Tesla anyways, is coming just simply from the drag coefficient, so the amount of energy that we need to push that car through the air. And the other really big thing that contributes to the rolling resistance of the car is its tyres. And just looking at the spec sheets for these cars, we can see that there is a huge difference in the tyres installed. So obviously there's lots of different specs of Tesla. I went for the tyres fitted to the Model S Performance, P100D type cars. So 245, 35, 21 on that listed as standard based on the information that I could find. Audi has a slightly wider tyre. So 255, 50, 20 on that car. So slightly wider tyre. And then the Porsche is wider again. And actually that's got a more kind of a classic race car type setup where it's got 265 35s on the front, 21-inch rim, and 305 30s on the rear on a 21-inch rim. So really big, wide tyres on the back there. Now, that's great for handling and for traction, but not very good for rolling resistance. There's a reason why the BMW i3 runs on tyres that look like they've been stolen from a bicycle. A wide tyre, if it looks like a steamroller tyre, it's going to have a really high rolling resistance. It's going to take more energy to push it. I think the tyre selection as well on out of the box, so the tyres that will have been measured, or the car's performance will have been measured on from an efficiency point of view, are more performance orientated on the Porsche and the Audi than on the Tesla. So, Porsche and Audi there have gone for performance over efficiency, just simply on the tyre choice. And what's really interesting here is because of how WLTP ratings are done now, you can actually see the difference that tyre sizes make on the same model of car. So if you look at the WLTP rating for an Audi, for example. There's a couple of different tyre size options listed there. And going from the widest option to the narrowest option makes 10% difference on the efficiency of the car. So 10% difference, you're looking at something like 28 watt hours there. So it's a significant difference in terms of pushing the car along, just simply in tyre selection. So, a more efficiency-orientated tyre on the Audi and the Porsche would probably make quite a bit of difference to the overall efficiency of the car. So we can see already, looking at the weight of the cars, the Tesla's got a little bit of an edge over the Porsche, but not loads. Looking at the drag coefficient, Tesla's definitely got an edge here, although it depends which spec of Porsche you're looking at, but clearly an edge. Both of those cars have got an edge over the Audi. And tyres, the Tesla is running on narrower rubber, which simply is going to be better from a rolling resistance point of view. And I can bet that Audi and Porsche have done an awful lot of work trying to work out what tyres they want on those cars to give them the best performance handling characteristics, probably more so than efficiency. I would guess has been their focus there. So that's kind of what I would say is the easy stuff in terms of efficiency out of the way. If we can deal with weight, we can deal with aerodynamic drag, we can deal with rolling resistance from the tyres. So we're now into like more in-depth powertrain stuff, the tricky bits. So the traction motor and the power electronics were the next kind of big thing in terms of a differentiator, in terms of how efficiently we can turn electrical energy stored in the battery into torque to move the vehicle. So I think there, perhaps somewhat controversially, the Porsche should actually be the most efficient car of the bunch. Now that uses two hairpin wound permanent magnet synchronous motors running at 800 volts. And it also has a really clever 2-speed gearbox at the rear that allows it to improve low-speed torque at the wheels for high-speed cruising. And Porsche seem to have managed to avoid the use of an oil spray system inside the motors, which is become common in a lot of hairpin motors to maximize continuous power, but it incurs a significant parasitic power consumption from the oil system. I could be wrong on that. From everything I've seen, they don't seem to have that on the Porsche. There doesn't seem to be any oil spray. It seems to all be water glycol cooling for the motors. So on the face of it, it looks like a really, really efficient setup. So interior permanent magnet motors, that 800 volts voltage level. So that means the current is reduced and the losses in the motors and the electronics are a function of the square of the current. So it's really smart going to 800 volts, and that's something we're going to see on a lot of vehicles in the future. And also that 2-speed gearbox. We've just done another podcast, actually, interestingly, about the use of multi-speed gearboxes and how they can help. And that 2-speed gearbox should be helping the Porsche to keep the motor in a more efficient operating point, and also if they're using it well under regen braking to generate more continuous power than you can with a single-speed transmission. So the Porsche powertrain, the motor and the electronics is really, really nice. There's no escaping from that. Side-by-side comparison with the hardware in a Tesla, there's a clear difference there. But actually, in my opinion, the Porsche would come out on top there. And a different kettle of fish if you're comparing to the newest Model 3, silicon carbide inverters, and the Model 3 also has interior permanent magnet motors as well. But the Model 3 still is at a much lower voltage than the Porsche. So the Porsche is always going to have that in terms of lower I-squared losses, lower ohmic losses in the electrical system. So, yeah, probably somewhat controversially, I think the Porsche powertrain is really, really smart. They've made some smart choices there, and they're just really interesting things. Model S, just as a reminder, I know lots of people know what a Model S looks like, but that has got two different motors. It uses a permanent magnet motor in the rear, IPM, and an induction motor up front. That was a change for Tesla. They used to have induction motors all round. The Model 3, of course, has permanent magnet IPM motors at the front and at the rear, but the Model S that we're looking at here, the performance car, has IPM in the rear and an induction in the front. The Tesla runs at 375 volts, so much lower operating voltage than the Porsche. So that means for a given amount of power in the motor, you're going to need to push more current into the motors on the Tesla, and electrical system losses are a function of I squared, so current squared. So actually, from a pure electrical conversion efficiency there, the Porsche should have an advantage. The Audi has a surprising setup for me in a lot of ways. So it has two induction motors, one at the front, one at the rear. They're running at 390 volts, so the voltage is a little bit higher. Induction motors aren't bad from a pure efficiency point of view, but for a given power and the kind of things we're looking at here, they tend to be a bit bigger and a bit heavier than the equivalent power or torque permanent magnet IPM motor. So you would say that the IPM motors in the Porsche and the Tesla are, basically a more power dense and therefore, in terms of a vehicle mass and efficiency point of view, a better option than the two induction motors, which are going to leave you carrying a little bit more weight than the IPM motors in the rear of the Tesla and all round on the Porsche. Of course, Porsche is the only company that's got a 2-speed transmission on the rear. There's a lot of reasons why they will have done that, but in theory that should allow them to keep the motors running in their sweet spot and really actually downsize the motor. So for a given amount of torque in a motor, actually what Porsche can do is they can switch into the lower gear and they can get that launch acceleration basically with a less torquey motor, but by using the gearbox to multiply the torque. They still need the power at high speeds, then they can switch into the higher ratio on the transmission, and they should be able to keep things running a little bit more efficiently and to optimize it there. The other kind of really important thing is, I'm kind of going, well, the Audi is not so great, it's induction machines, blah, 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 but when you get into the nuts of it, the efficiency on all of these setups is going to be pretty similar from an electrical point of view. The 800 volts over a driving cycle will give you the edge, but we're not talking about 15% difference. We're talking about maybe 2 percentage points difference in the powertrain setup, possibly 3 over a driving cycle. Actually, the Porsche is probably helping itself with the motors and the electronics. I would say the most efficient setup of the lot would be the Porsche, followed by the Tesla, and then with the Audi probably coming in third. But maximum over a driving cycle, just purely on the motor's ability to turn electrical power into torque, maybe 5% difference across the range. Now, there is, of course, a big difference where you get into calibration and where I talked about before braking system performance. Now, this would be interesting to know, and I will touch on this again later, but I think the Tesla is very well optimized in terms of how it recovers power under regen braking, particularly on the driving cycles. So basically, you don't want the hydraulic brakes to be doing anything at all. You want all of that to be being recovered and going back into the battery. And interesting in terms of the strategy that Porsche and Audi have used on their regen braking and actually how effectively they're managing to do that. Because in an electric vehicle, obviously, it's a big thing in terms of turning electrical power into torque to move the car. But then when you're doing regen braking, you're turning torque back into electrical power to charge the battery. The Porsche should have the edge there because it should be able to keep the motor running at its constant power point, higher power point for longer with a 2-speed transmission compared to a single speed reduction gearbox like the other two have. I do not know if Porsche are actually doing that, and I would be really interested to know if they have a shift pattern for regen braking or if they're actually not shifting during braking. And I have a suspicion they may be not shifting during regen braking because they're focusing more on consistent feel than maximum energy recovery. Okay, so on the motors and the electronics, the Porsche should have the edge over the Tesla and the Audi. Next up is a battery system and the charging system. So the Porsche is interesting. It's 800 volts, and actually that's better from a charging point of view. It means you can charge faster because the current is reduced. But actually, it does make it more complicated. So if you're plugging into a regular 400 volts charger, actually you need to do some clever stuff to get up to 800 volts to be able to charge the batteries. And there's a couple of different ways of doing that, and Porsche are using both. So they are splitting the battery pack sometimes when they need to, and other times they're using a boost converter in the powertrain. That will be hurting them a little bit from an efficiency point of view because of some step-up losses there. I could not find any information at all about what mode of charging was being used to charge the cars on the WLTP measurements, so what the charging source was, and then therefore what onboard charger mode was engaged. So I'm going to have to do some more investigation into that point. But in theory, the 800 volt system should help. But actually, because of power conversions and things, if you're charging it from a regular charge point, it might actually be hurting you. The other thing, just to touch on again, I mentioned it earlier, but charging strategy, I really do think helps to drive some of the reasons for Audi walling off as much battery capacity as they have. I suspect in the performance attributes for that car, they were making a big deal about charging time and charging performance. So the engineers took a decision to basically restrict the point at which the battery charges to, so they could then claim a really fast recharging time, because we're not having to tail off the charger as we're charging the car. Now that won't have affected efficiency, and that's what I'm talking about now on this bit, but just to sort of mention that while it's in my head again. So it was a big thing that Audi made a big point about on the charging system. I think though, when you get into the battery, we can really start to see a big difference between the engineering on the German cars and on the Tesla. So Tesla use cylindrical cells. There's a cooling system that is embedded in amongst the cells. So on the Model S, a serpentine pipe that winds through the battery box. Slightly different on the Model 3, but same kind of principle. No serpentine pipe on the Model 3, straight tubes instead. But the Model S that we're looking at here, there's a serpentine pipe that runs through the battery box. The cells are cylindrical. They're arranged around the pipe. The Audi and the Porsche have actually quite similar batteries when you look at them and you look at the cutaways of these battery packs. They have really, really substantial battery structures compared to the Tesla. So when you look at the battery box structure on the Audi and the Porsche, it's absolutely huge. There's a very large cooling system in the base of the box, and you can see that box has been designed so that basically the cell modules kind of drop into it, but we're not expecting the cell modules to have any structure or do anything useful. They just sit in that tray, and they're held in position. They're cooled from the bottom down. That's kind of the wrong place to cool a battery from, but they're just doing bulk heat removal from the bottom of the battery units there. And the modules are much more kind of walled off, segregated than they are in the Tesla. So you look at a Tesla battery pack, there's a very integrated, compact unit. Cylindrical cells are all really close together. Serpentine pipe runs through. Stuff's kind of glued to each other. It's all fairly self-supporting. There's quite a bit of use of the part of the battery pack as structural elements themselves. And then obviously it's combined. It's held in a box. Interestingly, the Model 3 has gone another level again, and they've got rid of an awful lot of the structure in the battery box on the Model 3, and it's basically a couple of quite simple sheet metal pressings covering the battery, and there's no kind of big structure. Like there's a bit of a structure on the Model S. On the Porsche and the Audi, though, the battery boxes are absolutely massive. They're using pouch cells, so standard pouch cells that are then being packaged into modules, and the modules drop into the battery box. Now, I think if we just kind of circle back a little bit, I mentioned before about charging performance and rapid charging, and maybe that's why they're walling off a bit of the battery capacity because of temperature management, etc., etc. Now, looking at it, I think the performance of the cooling system under really high currents on the Audi and the Porsche will not be quite as good as in the Tesla. So the Tesla's not a massively advanced cooling system in itself, but basically the bit that gets hot on the cell is the tabs. So with the tabs where the current is mainly concentrated and flowing, that's the hottest point on the cells. On the Audi and the Porsche, we're cooling the bottom of the battery tray. We're not up in amongst the cells themselves. We're quite a long way away from where the tabs are on the cells. So actually, we are doing some bulk heat removal, which is helpful. We're kind of, because of how the pouches are lying in the battery box, we're kind of cooling the edges of them, the sides of them. But we're not really in amongst the cells from a cooling point of view. On the Tesla, we're really in amongst the cells from a cooling point of view. There's because the cooling runs through the middle of the pack. We've got bus bars on either side of the cooling jacket, so the proximity is closer, probably a better thermal pathway from the bus bars to the cooling pipes, and kind of more surface area inside the battery pack to pass coolant through and to cool those cells. So I think the design of the battery boxes themselves, so not only add a lot of weight to these cars, that probably actually result in less heat transfer away from the cells under high current flows, which probably goes back to explain certain level of the walling off on the battery. So if we don't want to push the cells quite as hard, we want to make sure they don't get too hot. And actually, if we can't get heat out of the areas that's needed, we're relying much more on sort of the heat capacity of the components in the pack and like bulk heat removal. I think there's quite a significant difference there in terms of the design of the cooling system in the battery packs. It's then having a number of knock-on impacts on other parts of the vehicle. So that's the battery. The Tesla's definitely got the edge on the battery. On ancillary systems, so this is we're almost there in terms of the key drivers. So this is the supporting systems on the vehicle. So things like the HVAC, the cooling, the steering pump, these all consume power, and this parasitic power consumption reduces range. So we're not using electrical power to drive the vehicle now. We're using electrical power to keep all the components cool, etc., etc. So parasitic power consumption can be quite a big part of the overall power consumption, particularly on these fairly lightly loaded driving cycles, the WLTP driving cycle against the standard profile. Porsche and Audi have made a big thing about the cooling systems in their cars and about how they've got more cooling capacity, and Porsche did a big thing about that you can do more super fast accelerations than any other car. Audi have done a big thing about they've actually made some statements publicly about cooling capacity and consistent performance. So I think they're gunning for the Tesla's cooling capacity. And, in early Teslas, it was a bit of a weak spot. I think a lot of that has been corrected in the vehicles and actually through software updates as well, interestingly, rather than hardware updates. But the key thing here is, so whilst a big deal has been made about the ancillary systems by the OEMs, when I look at these cars, there's not a huge difference. And in particular, so you could say some of the components are a bit bigger in the Porsche and the Audi than they are in the Tesla, maybe a bigger pump, etc., etc. But interestingly, when it's on a WLTP test cycle or even on the EPA test cycle, which is a bit harder, it's quite a lightly loaded test cycle, really, compared to the maximum performance potential of these cars. And they've all got super smart, controllable electric pumps, controllable electric fans, multi-way valves so they can make sure coolant is flowing in the right places at the right time. And actually on the standard test cycle, I don't think there'll be a huge difference in terms of the parasitic power consumption of one cooling system versus another, because essentially that driving cycle isn't stretching the car anywhere near as much as harder driving where you're using the full performance potential of those cars. And the WLTP arguably doesn't really reflect the real world driving conditions, EPA test as well. Particularly in cars as powerful as these, it depends why you're buying one of these cars, but even the Tesla is an absolute rocket ship. If you're using that performance day in, day out, you obviously would not get anywhere near the range of the car. Another thing actually that's interesting to watch, and it's very hard to track down this information and tie it all together, is the difference in terms of the vehicle performance on WLTP and the total performance. And looking at those two, you can see how efficient the charging process is for the vehicle. I'm not going to go into too much detail on that here because we're rapidly running out of time. But maybe that will be for a future podcast. So, to summarize, what's the conclusion? So stop rambling on, Ryan, and get on with it. What is the conclusion? So there's a clear difference between these cars, between efficiency and range. One drives the other. Lots of commentators seem to have been interchanging efficiency and range, and I think it's confusing, or perhaps a sign of their confusion themselves, but there is a clear difference between the cars. The powertrain on the Audi is probably a miss for me. It seems strange to have launched an EV that's completely new to the market with induction motors at this point, particularly at this price point. The motors are going to be relatively bulky and heavy for their given performance. In my opinion, they don't really represent the state of the art, although they do have a really intricate cooling system in the motors, which I think is a really neat design. The battery in the Audi looks to be very heavily, dare I say it, over-engineered, or maybe just not very well thought out. Each element has clearly been treated in isolation rather than looking at the thing as a whole, as a system. So that means it's very large, relatively heavy structure, cooling that won't be doing all that much in areas that matter most. So whilst relatively heavy, though, it won't be all that inefficient when under power. So, that's not really where the performance delta is coming from. I talked earlier about the efficiency difference between all of these drivetrains is not going to be massive when you're talking about under power. I think the weight difference really is coming in no small part from the massive battery and the battery tray structure that's been engineered, to protect the cells and every possible eventuality. This extra weight, the rolling resistance, and the aero basically stack up pretty much to describe the efficiency deficit. And then the conservative regen strategy, I think, making up the balance. So basically, if they were being a bit more aggressive in terms of how they were bringing regen in on the driving cycle, they probably could recover some more energy, which would give them an overall more efficient drive cycle result. So I think that is the final kind of thing that's making the efficiency difference. And then the final bit in terms of why the range is so far off is the massive, massive headroom they are allowing for in the battery. So yeah, the Audi, it's a pretty looking car. I'm sure it's a very, very nice place to be inside. It's going to be great for a lot of people, but for me, it doesn't quite hit the mark. The Model S still does have an induction motor at one end. The Model 3 doesn't. It's dual IPM. But, the Model S apparently is going to be upgraded soon. The new version has been bashing around the Nürburgring, and that's a whole other topic. Don't get me started on the Nürburgring. The new plaid powertrain, and that's, maybe 2 IPM motors on the rear and 1 on the front, so getting rid of a rear diff and da-da-da. We're not talking about that in this podcast. That is a really interesting powertrain. We've had we've actually done another podcast a while ago talking about why that dual motor on one axle approach was a good thing. Maybe someone from Tesla was listening and they decided to implement that in their plaid powertrain. I don't know. If you're from Tesla and you listen to this podcast, let me know. I think though, so to get back to the point, controversially maybe the Porsche powertrain is really, really good. The 2-speed gearbox on the rear. But the WLTP and the EPA test cycles are showing the car to be quite a bit worse than the Tesla in terms of range and efficiency. I think the asset of the 2-speed transmission possibly isn't doing much for it under this mild testing conditions. It may be even making the cycle efficiency slightly worse because you're carrying the weight of the transmission. And I guess Porsche probably not doing too much to optimize shift patterns to maximize regen power. I do believe, though, that it'll be a really big asset to this car under more aggressive driving conditions, delivering some fantastic performance, also helping to get the best out of the motors and keep them running in their sweet spot. I think I'm pleased that Porsche have kept this feature on the car. It's kind of the easy thing to go to a single-speed transmission. 2-speed has got a lot of benefits, and it's really good to see Porsche using that on the car. However, where the Porsche is not so good is, again, in the battery. So very similar arrangements to the Audi, big chunky structure, drop-in modules with pouch cells, poor use of the available space, cooling kind of in the wrong place, not really getting to the points they need to. So a bit of extra weights they're carrying in the battery pack compared to the other car. So fundamentally, though, from a pure conversion of energy into motion point of view, I think the Porsche will be the leader here, and will actually be doing better than the current Model S. In fact, should be slightly better overall. I think a lot's been said about the OEMs about parasitic power consumption. I've talked about that already. I don't think it's such a big thing on the WLTP test cycles. I think a big deal has been made about it, but I don't think it's a huge deal. The WLTP is not stressing the car out enough to get anywhere near needing the full power capacity of the cooling system on the car. The efficiency difference definitely lies elsewhere outside of that the parasitic power consumption of those systems, unless someone's just done a really bad job and messing things up. A really big clear difference is the tyres. So Porsche definitely got higher rolling resistance there, steamroller-esque rubber on the back of that thing as it glides silently out of the factory. So yeah, I think that then Porsche and Audi are both playing it very, very safe with the regen strategy and the battery headroom strategy. They've publicly discussed this in terms of powertrain thermal management and all that extra weight they're carrying around in a battery pack that they're not using. So I think, strategically, the Porsche should be a fantastic option, very well engineered, heavily engineered battery pack. But I reckon if you actually optimize the battery pack in the Porsche, you probably could take more than 100 kilograms out of it, which then would make it very competitive weight wise with the Tesla. There's other things you could do as well in terms to reduce copper content and take weight out elsewhere in the car. I mean, just the tires and the wheels are carrying significant amount of weight on the Porsche. Yeah, Audi and Porsche definitely, though, effectively want to deliver super consistent performance over every possible operating scenario. And I think they've basically decided to make some compromises now to basically say, you know what, we're not going to go for stretching the range and cycle optimizing these cars. We want to go for super consistent performance. We see that as being the Achilles heel on the Tesla. You know, when these cars were being developed, it was at a time where people were sticking videos on YouTube of Teslas turning them derating on the Autobahn because the batteries were overheating and stuff like this. I think maybe they've played it a little bit too safe there, and essentially that's really what's driving the performance. We can take apart the performance delta, and we can see on the Audi exactly where all that's coming from. It's a bit harder to see on the Porsche where the efficiency is coming from. You know, tires are going to be a big part of it, but certainly not coming from a lack of efficiency in those really nice IPM motors that they've got under there. So, yeah, I think much has been made of this. I think the Porsche is a really good powertrain. I suspect that if you put a Tesla on some equivalent tyres and did some driving tests around a track and looked at efficiency on a comparable kind of high-performance driving cycle, I think that the Porsche actually would beat a Tesla from an efficiency point of view. Now, again, that's controversial, and I'm sure I'm going to absolutely lynch for that, but that is my opinion. I think the Porsche, under a more aggressive driving cycle on like-for-like tyres, would be a more efficient car than the current Tesla, and that's what I'm comparing to. I'm not talking about the Plaid powertrain or what's coming. I'm not talking about the Model 3. I'm talking about the current Model S that I compared to here. If anybody, by the way, wants to lend me a Taycan and a Model S to set up that back-to-back comparison test, I would be really, really happy to do that. I'm sure I can make that. I'm sure I can make that happen, and it'd be interesting, perhaps, to get that data. So I think for now, the moral of this is kind of not reading the headlines, looking a little bit deeper beyond that. There are some clear differences in these cars, and the approach basically seems to mostly be coming back to the battery. So Tesla's edge is still that it's got a really good battery. It's able to use more of the installed capacity of the battery pack as usable capacity, and a much lighter weight battery structure on the car than the other two. So that's definitely Tesla's strength. Porsche, very, very good from a powertrain point of view. You know, that efficiency of those motors and the electronics you will not beat with a 400-volt system. So very, very good to see that in the Porsche. Audi, kind of, yeah, they've launched a car that's a little bit out of date, but, you know, not bad as a first effort. If efficiency and range are your most important characteristics, the Audi is definitely not going to be the car for you. There are better, lighter cars out there. So that is it for today. Hopefully that has made some sense, and I haven't completely rambled around too much, and we've followed a fairly logical track there. That's all we've got time for. I really, really hope you've enjoyed the podcast today. You've got some value and some use out of it. Please don't forget to leave us a rating or a comment or hit like. We've been getting some absolutely fantastic ratings recently. The podcast is really going from strength to strength. So we're inside the top 10, most of the podcast charts for tech podcasts now. Number 9 in the US, the other week, number 6 in the UK. So do keep sharing this with people and letting people know about it. We've got some really exciting episodes coming, some great interviews with some people who are experts and leaders in their field. That is all coming. That's all I've got time for today now, though. Thank you very much for taking the time to listen to me.